compound inequalities today. There are two types. Some compound inequalities have more than one inequality symbol. And sometimes you use the word and, sometimes you use the word or. Here's a compound inequality because it has two symbols. This really says two things. You don't need to separate them unless you just want to. It says 3 is less than 5x minus 13. And the way this is written implies and also 5x minus 13 is less than or equal to 7. It's two parts. But really, for purposes of solving it, in order for an and inequality to be true, both pieces of it have to be true. In order for an or inequality, we'll get to in a minute, in order for an or inequality to be true, only one piece or the other has to be true. So on this one, in order to solve it, you really don't want to go to the trouble of splitting it up and saying this really says two things. You can solve it all at one time. If you ignored this symbol and you were just working with 3 is less than 5x minus 13, what would you do?
Add 13.
Yeah, add 13 here and here. And if you were solving this piece, you would add 13 here and here. So you can take care of it all at the same time. Add 13, add 13, add 13. And 16 is less than just 5x. Those go away. Is less than or equal to 20. And then, if you were solving this much of a compound inequality, you would divide by 5 on both sides. And if you're solving this much of it, you would divide by 5. So you can take care of it all at the same time. And then 16 fifths is less than x is less than or equal to. Go ahead and reduce and call that 4. So here's the algebraic solution. I also want a graphical solution. So for graphing purposes, 16 divided by 5 is 3 with 1 left over. So for graphing, from 3 1/5 up to 4, not including 3 1/5 or 16 fifths, but do include 4, so remember the brackets indicate included. As long as we pick a number in this interval and plug it into that inequality, it will make it true. We'll check one in a minute. So I want an algebraic solution, a graph, and then interval notation solution. So the interval notation is really almost the same thing as the graph. Describe where can you look on the number line. Where do you have to look? You have to look from 16 fifths, not including 16 fifths, up to 4 and including 4. And as long as you pick a number in here to plug into the original sentence, it will make it true. Here's another one. This is an implied and inequality. It says two things. It says -4 is less than 6x minus 9, and 6x minus 9 is less than 12. But I don't really want to pull it apart and make it two separate inequality sentences because it's easy to solve this one all at one time. If you were going to solve that, you would add 9 in the middle and on the left. And if you were going to solve this, you would add 9 in the middle and on the right. So we can take care of that all at the same time. So -4 plus 9, 5 is less than 6x, 9's go away, is less than 21. And then, if we were solving this, we would need to divide both sides by 6. And if we're solving this, we would need to divide both sides by 6. So 5/6 is less than x, is less than, we should reduce that. It'll reduce by 3, so call it less than 7/2. If you draw a picture of the solutions, 5/6 is a little less than 1. So 5/6, and then you would hit 1, 2, 3, 4. 7/2 is 3 1/2. So from 5/6 up to 7/2, as long as you pick a number in here and plug it in, it will make it true. So let's just try that. What if we take 2? Because it's definitely in that interval that we shaded. If you plug in 2, 6 times 2 is 12. 12 minus 9 is 3. So that would give us -4 is less than 3. That's true, right? and 3 is less than 12, that's also true. What happens if you pick a number not in the interval, like say 5? If you do 6 times 5, that's 30. 30 minus 9 is 21. Is negative 4 less than 21? Yes, but is 21 less than 12? No. In order for the inequality, the compound inequality to be true, since and is implied, in order for it to be true, all of the pieces have to be true. So the solution notation, as long as you pick a number, starting at 5, 6, not including 5, 6, going up to but not including 7/12, it will make that sentence true. When you get to 3 and 4, I think this is actually number 1 again. When you get to the second examples down at the very bottom, these compound inequalities have the word or between them. So if I wanted to talk about Tucker, if I say this, her name is Tucker, or she has black hair, have I said something true? If I look at you and I say, your name is Tucker, or you have black hair, have I said a true statement?
Yes.
Yes, because as long, with the word or, as long as one of the pieces is true, the whole statement is considered true. So, her name is Tucker, yes. She has black hair, no. But one or the other of the pieces is true, so the whole thing is true. So for or, just one piece has to be true, not both. You can't solve or compound inequalities all at one time, so you have to work each part separately. So subtract 1 from both sides. 3x is less than negative 9. Then divide both sides by 3. And x is less than negative 3, or solve the other piece. Add 2 to both sides. 5x is greater than 16. And then divide both sides by 5. X is greater than 16/5. When you graph this, when you make a picture of where you look on the number line to find numbers that you can plug in and make that a true sentence, you have to look, start at negative 3, don't include negative 3, but everything to the left. Or 16/5, remember that's 3 1/5. Start at positive 16/5, and everything to the right. So in interval notation, when you have a split graph, you can't do both of these things at the same time. So where do you look to find solutions? You look on the interval that comes from negative infinity up to negative 3. And then you join that with the piece coming from, and so we use a thing that we call union. It kind of looks like a U, joined with the piece that starts at 16/5 and heads to positive infinity. So if I pick a number over here, like say negative 5, if I plug negative 5 into this first one, 3 times negative 5, negative 15. Negative 15 plus 1, negative 14. Negative 14 is less than, it's farther to the left, than negative 8. If I plug negative 5 into this one, I'll get negative 25 minus 2. Negative 27 is not greater than 14. But when I plug in negative 5, I make this piece true, not this piece, but as long as one or the other of the parts is true, the whole sentence is considered true. So here is your algebraic solution, your graph, and interval notation. And I'm going to ask you for all of those. Work on this one. It's an or. You can't solve it shortcut style. You have to just work each piece separately. I miscopied this problem. On your notes it says 7x minus 3. Did you agree with me? X is less than 3/7 or X is greater than 4. There's the algebraic solution. I need a graphical solution. Give me 0 as a reference. Here's 4. Everything greater than 4 or less than 3/7. If you pick a number from either one of these places, it will make one or the other of the pieces true, which then makes the whole thing true. Is still okay? So interval notation, the solutions start, they come from negative infinity up to 3/7, not including 3/7, and you join that with the piece from 4 to infinity. You okay on compound inequalities? Eddie, what's the matter?
I thought it wasn't included.
Did I miscopy it? Oh, it is included in this one, isn't it? It's an or equal to on this one, so it should have been this. Thank you for that. Now y'all agree? Okay. Last page. So here's what we've done so far. With inequalities, we have solved simple inequalities. The only thing you got to remember is if you multiply or divide by a negative, you got to reverse the symbol. And then compound inequalities have 2 inequality symbols. And then absolute value inequalities is on the last page. So on the top of your notes, there are 3 inequalities. You have absolute value of x is less than or equal to 3. You have absolute value of x is greater than or equal to 3. And then you have absolute value of x equals 3. Let's do the last one first. Absolute value of x equals 3. Definition. The absolute value of a number is its distance from 0 on the number line. Distance is always positive. So on this last one, you have to look at the absolute value bars and think, okay, distance. Where would I have to be standing if I'm on the number line in order to be a distance of exactly 3 away from 0? 3 or negative 3. Absolute value has 2-part solution. If I want the distance away from 0 to be exactly 3, I have to be standing on negative 3 or positive 3 if I'm walking on the number line. So the solution on this one, there's the graph. It's not an entire interval, it's just 2 distinct locations. X is either negative 3 or X is positive 3. We've done absolute value equations before. They always have 2-part solutions. If you check it, let's see. If I plug in negative 3 where I see an x, absolute value of negative 3, that's saying how far is negative 3 away from 0? 3. Absolute value of positive 3, how far away is positive 3 from 0? 3. Are you okay? Now, do this. On this one right here, I want you to draw a picture on your notes on a number line. And this problem says, find all numbers whose distance from 0 is either exactly 3 or less. Draw a picture on your notes of what that would look like if your distance from 0 is either exactly 3 or less than 3. Where could you be standing if you're walking the number line? If the distance from 0 is either exactly 3 or less than 3. And then shade your number line. here's the picture I was looking for. If the distance away from 0 is exactly 3, that puts you on -3 or +3. And a distance of less than 3 means, keyword I was hoping somebody would tell me is somewhere between. If you're standing on -1, you're 1 step away from 0. If you're standing on -2, you're 2 steps away from 0. If you're standing on -2.9, you're 2.9 steps away from 0 in the direction to the left. So if you want the distance to be less than 3 away from 0, you're staying pretty close to 0. You're staying within boundaries between -3 and +3. So anytime you see less than, think less than means between. So set up a between sentence. Question? Set up a between sentence. Could you do it as 2 separate sentences? Yes, but the easiest thing for you to do is set up a between sentence, and it's always this: small number on the left, big number on the right, variable in the middle, and less than or equal to match this both times. This really says 2 things. It says I can have numbers that are, if I'm reading X as numbers, X can be numbers that are bigger than -3 and numbers that are smaller than +3. This really says 2 things. But between is the shortest way to talk about it. So here's my graph. Here's the algebraic solution. In interval notation, go from -3 to +3, including both ends. Now draw a picture on this one. This is absolute value. Draw a picture on the number line. If absolute value is greater than 3, absolute value means distance. Draw me a picture of what it looks like if you're a distance of more than 3 away from 0. Question?
I'll ask you about it later.
Okay. You can ask.
No, I mean, yeah. It'll take a long time because I'm very confused.
Okay. If the distance means, you just have to think, how far away from 0 am I? I'm 1 away. That number's okay. 2 away. If I'm standing out here on 10, how far away from 0 am I?
10.
So that can't be included in numbers whose distance is less than 3 from 0.
But what about the -3? Can't you keep going the other direction?
What if I'm standing on -10?
You're 10 away.
I'm 10 away. I want to be less than 3 away. I want to be exactly 3 away or less than 3 away.
Okay.
Does that make sense? That makes it better?
Yeah, that makes sense.
So draw me a picture. What does it look like if the distance from 0 is greater than 3? Shade the number line. Remember, you can go more than 3 steps in both directions. You can go more than 3 away on the left, but you can also go more than 3 away on the right. There you go. So here's the picture I'm looking for. Several of you have this. If the distance is exactly 3 away, you know you're on +3 or -3. If the distance from 0 needs to be more than 3 steps, 1, 2, 3, 4, I gotta be out here somewhere. Or I can go 1, 2, 3, 4 and be out here somewhere. Anywhere on these 2 intervals, my distance from 0 is greater than 3. Does that make sense? Now, the distance from 0 is greater than 3. But what kind of numbers are we talking about? To the left of -3, -3, -4, -5, -6. What's happening to those numbers as you move to the left?
You're small.
These are numbers that are getting smaller than -3, while these numbers, as you're going to the right, those are numbers that are getting greater than +3. You have to have an or. In interval notation, when I describe these These are numbers that come from negative infinity up to and including -3. And then we join two pieces together, two solutions together, so union from 3 to infinity. So on number 4, the plot thickens a little bit because no longer do we have just x inside the absolute value bars. The key on solving absolute value inequalities and equations is to remember they have two-part solutions. So, what does it mean? What would it look like if your distance from 0 was more than 14? I'm going to draw you a little picture. This is not a graph of the solutions to the whole inequality, to the whole absolute value problem. It's just, what does it look like if I'm more than 14 away from 0? I can go out 14 to the right or beyond. I can go out 14 to the left or beyond. So I can be standing on numbers that are to the left of -14, or I can be standing on numbers that are to the right of +14. Now what's happening with these numbers? Their distance from 0 is more than 14 both ways, right? But the numbers themselves, what's happening? -14, -15, -16. What's happening? You're getting smaller as you go to the left. You're getting bigger as you go to the right. So whatever is inside of this absolute value bar, you never rewrite the absolute value bar when you split it into two pieces. 3x plus 5 has to turn into a number that's smaller than or exactly -14, or 3x plus 5 has to turn into a number that's greater than or equal to +14. We have to solve this in pieces. So if we subtract 5 from both sides, 3x is less than or equal to -19. Divide both sides by 3. X is less than or equal to -19 thirds. Or, solve the other one, subtract 5 from both sides. And 3x is greater than or equal to 9. And divide both sides by 3. X is greater than or equal to 3. So here is a picture of my final solution. -19 thirds, what's that? -6 1/3. So for graphing purposes, -6 1/3 or 3. So here's 0. I've got to be bigger than or equal to 3. Or smaller than or equal to -19 thirds. -6 1/3. Let's pick a number and make sure we're right. So let's pick something over here. Like say 5. Y'all with me? You okay? So if we pick 5, 3 times 5 is 15. 15 plus 5 is 20. Absolute value of 20 is 20. Is 20 bigger than or equal to 14? Yes. Pick something over here. Give me a number. Somebody tell me. -7. So if we plug in -7, 3 times -7, -21. -21 plus 5, -16. Absolute value of -16 is 16 bigger than 14. Yes, it is. So numbers over here work. Now let's try one of these. What number should we try in our non-solution spot? Try 1. 3 times 1 is 3. 3 plus 5 is 8. Absolute value of 8 is 8. Is 8 bigger than 14? We didn't expect it to be so because it was not in our solution interval. So here is your algebraic solution. And then give me a graph. And then give me interval notation. Interval notation means we come from -infinity, it's from left to right, from -infinity up to -19 thirds, including -19 thirds. Then we join that piece with the one that starts at +3, including 3, and goes to infinity. Question?
So, when we have that two answers, like at the very beginning, You have to switch the signs over when it's a negative?
Over right here?
Yes.
Yes. Because it's gotta be, it's to be farther out than 14, away from 0, the numbers that you're standing on have to be getting less. So, less than means the symbol points to the left. So less than, smaller than negative 14, or you gotta be getting bigger going to the right, bigger than positive 14. So yes, you're exactly right. When you have an or, the symbols are gonna point like this. One is gonna be less than a negative or greater than a positive. So number 5. On this one, we got absolute value of 4x minus 9 is less than or equal to 23. So the first thing you should look at when you have an absolute value problem to do is right there. No absolute value means distance. Distance needs to be either exactly 23 from 0, which would mean where could you be standing if you're exactly 23 from 0? Negative 23 or positive 23. In order to be less than 23 away from 0, you're going to be standing in between those, right? Anything on the inside of those. If you draw it, so less than means between. If it's a less than, then the easiest way to do it, instead of writing 2 separate problems with and, just do between notation. Small number on the left, big number on the right, 4x minus 9 in the middle, and less than both times. And these kinds you can solve all at once. Add 9, add 9, add 9. So then negative 23 plus 9 is less than or equal to just 4x, because those are gone, is less than or equal to 32. And then divide by 4, divide by 4, divide by 4. Reduce, because that doesn't divide evenly. Negative 7 halves is less than or equal to x is less than or equal to 8. So if we draw a picture of where to look, here's 0, up to and including 8. Negative 7 halves is negative 3 1/2. And everything in between. So if you pick something to test it, like say 5, 4 times 5 is 20. 20 minus 9 is 11. Absolute value of 11 is 11. Is 11 less than 23? Yes. Let's pick something over here that's not in our solution, like maybe negative 5. Because this goes up to negative 3 1/2. 4 times negative 5 is negative 20. Minus 9, negative 29. Absolute value is negative 29. 29. Is 29 less than 23? Doesn't work. So where do you look to find numbers that you can plug in and make this a true sentence? You got to start at negative 7 halves, including it, and go up to 8 and include it. So that was 5. Look at 6. On 6, absolute value of 2x plus 1 is greater than or equal to 7. Absolute value inequalities always have 2-part solutions. So greater than, what does it look like if the distance from 0 is greater than 7? Hey Daniel, we're on the 1.7 notes. I'm recording it so you can catch up with me. But get those out and we're on the back page number 6. As it turns out, if you want the distance to be greater than 7 away from 0, it's a split graph. So when you see greater than, we're going to think great or. An or graph is a split graph. If I draw you a picture of what it looks like to be more than 7 away from 0, here's 0, here's 7, here's negative 7. I've got to be out past positive 7 to the right or out past negative 7 to the left. Do you agree? Either of those spots, I'm more than 7 away from 0. So if I split this into 2 parts, I will either say 2x plus 1 is less than or equal to,
-7.
or 2x plus 1, whatever's inside will be greater than or equal to 7. Now it's solved two pieces. The hard part's setting it up, and once you understand the idea of setting it up, if it's a greater than, it's an or, your symbols are gonna do this. So if you subtract 1 from both sides, then 2x is less than or equal to -8, and when you divide both sides by 2, x is less than or equal to -4, and if you subtract 1 from both sides, 2x is greater than 6, x is greater than, it should be an or equal to, greater than or equal to 3. So this was not the solution, this was just what helped us set it up. Now if I graph the solution, where do I look? I look at x's that are less than or equal to -4, -4 and to the left, 0, greater than or equal to +3. So if I describe these intervals where I can look, it's from -infinity up to -4, including -4, and then we join that with the piece from 3 to infinity. Are you okay? Look at number 7 right quick. The first thing you should look at is this symbol. Less than means between.
Hi, this is the last call for any student